Hello students, this is Shailaja Vibhute. Today let us start 6th chapter, Electromagnetic Induction. If current flows in a conductor, it is called current carrying conductor. Around this current carrying conductor, there exists magnetic field. If you change the current, definitely magnetic field around the conductor changes. So this is very basic thing. Based on this, let us learn what is this electromagnetic induction. See the word there, electromagnetic induction. So when magnetic field changes, electric current induces. This phenomena is called electromagnetic induction. So what is electromagnetic induction? It is a phenomena of generating electric current by varying magnetic field, by changing magnetic field. So when magnetic field changes, current induces. This phenomena is called electromagnetic induction. Okay? So to get more idea about this electromagnetic induction, we should know about magnetic flux. So let us see what is magnetic flux. Magnetic flux can be defined in two ways. First one is like electric flux. It is number of magnetic field lines passing normally across unit area. So what is magnetic flux? The number of magnetic field lines passing normally across unit area. Even we can define it with the help of a mathematical form, that is, it is defined as the product of the component of magnetic field along the normal of the surface and area element. Means what? Flux is denoted by the letter phi. Okay. So since it is magnetic flux, so you can use the letter phi B. B is for magnetic field. If you write it as E, capital E, it becomes electric flux. So since it is magnetic flux, you can take the letter B. So phi B is equal to BA cos theta. So component of magnetic field along the normal of the surface means what? B cos theta. Area element is nothing but it is A. So phi B is equal to BA cos theta. It is expression for magnetic flux. Now let us see how to get expression for magnetic flux. For that you have to take one small diagram here. Say this is one area which you have marked. Okay. So for this area, say let us apply the magnetic. This is the magnetic field. B represents magnetic field. And this represents area. This is area. Okay. In between this area element and this B, angle theta is made. Now see the terms here. Let A is area of the plane surface. This A is area of the plane surface. B is magnetic field. Theta is angle between the directions of area A and B. Okay. Now by the definition of magnetic flux, phi B is equal to what? BA cos theta. So this BA cos theta can be written as B dot A. I hope dot product and cross product you are remembering. This is actually vector B dot vector A you have to take. This vector is not clear here, so you write it as vector B dot vector A. It is a dot product, so it is nothing but BA cos theta. Okay. So how to get expression for magnetic flux? It is nothing but according to the definition, phi B is equal to BA cos theta. BA cos theta is nothing but it is dot product. Okay. So SI unit of this magnetic flux is Weber, W-E-B-E-R, Weber. You can write it as capital W, small b. So SI unit of magnetic flux is Weber, or you can write it as Tesla meter square. Tesla is unit of magnetic field. You will get it, okay. And this magnetic flux is, whether it is a scalar or a vector quantity, magnetic flux is a scalar quantity. So since you are telling number of magnetic field lines passing, number means definitely no direction, so it must be a scalar quantity. So magnetic flux is a scalar quantity. Okay, remember this. Now to demonstrate this electromagnetic induction with the help of an experiment done by Faraday, let us take one experiment here, that is magnet and coil experiment. So this magnet and coil experiment, it gives the idea about electromagnetic induction. So in this magnet and coil we are saying means, first let us take the diagram. So you are observing in the diagram, this is magnet, it is called bar magnet. So bar magnet, it has two poles, one is north pole, another one is south pole. So N is north pole, S is south pole, okay. So this is one bar magnet. Now we have to take one coil, okay. So you can take one wire, copper wire, and take number of turns, so it becomes a coil. C is coil now, okay. Ends of the coil, to this ends of the coil you can connect one galvanometer. So what is galvanometer? It is an instrument which is used to show the presence of current. It detects whether current is present or not. So galvanometer is connected to ends of the coil. So this is coil and this is bar magnet. Now what we have to do? You have to move this bar magnet inside this coil. What Faraday was observed is, when it is moved inside the coil, this galvanometer shows some deflection. Okay. It is showing some deflection means what? Current is induced. Current is flowing in the coil. When magnet is moved away from the coil, it is taken out of the coil, then galvanometer comes back to its initial position. This pointer of the galvanometer comes back to initial position. Means what? Current reverses its direction. Okay. So the arrangement consists of a coil with galvanometer and a bar magnet. Okay. When the north pole of a bar magnet is pushed towards the coil. So when north pole means this one, N. When it is pushed towards the coil, galvanometer shows the deflection in one direction. This indicates that the current induces in the coil. Okay. When the magnet is brought to rest, now immediately instead of taking out of the coil, keep the magnet like that only. Means when it is at rest, deflection in the galvanometer reduces to 0. Means when the magnet is brought to rest, deflection in the galvanometer reduces to 0. When the magnet is pulled away from the coil, the galvanometer shows deflection but in the opposite direction. So this indicates that current is induced but it is in opposite direction. Okay. Similarly, same results you can see. Instead of north pole, if you take south pole of the magnet, and if it is moved towards the coil and if it is moved away from the coil, then also in the galvanometer you can observe the deflections. Okay. But if you keep both magnet and coil at rest, deflection you cannot see in the galvanometer. Why? Because if you are not moving the magnet or if you are not moving the coil, then there is no change in the magnetic field or magnetic flux. If magnetic flux changes, then only current induces. So if you see the last point here, when the coil is moved keeping the magnet at rest, the same effects are observed. Means what? In above 4 points, you have moved the magnet, but coil, it was kept at rest. Correct? So when magnet is moved towards and away from the coil, you are observing the deflections. But the same results you can see by keeping magnet at rest, but you can move the coil. If coil is moved, then also you can get the deflection. Means what? Either magnet should be moved or coil should be moved to get the induced current. You can see here in the experiment, when the magnet is moved inside the coil, you are getting one deflection in the galvanometer. When it is moved away, the deflection is showing in opposite direction of previous one. Okay, I hope it is clear. See this one. This is galvanometer. Okay, this is galvanometer. In this galvanometer, you are seeing the direction. Okay, see here. This red color pointer is moving one side and next another side. So this is a demonstration for the experiment, that is magnet and coil. I hope you have understood the experiment now. So either magnet should be moved or coil should be moved to get the deflection in the galvanometer, or to get the induced current, there must be change in magnetic flux. So when magnetic flux will change? When there is a change in, see in this diagram, if you observe this diagram, these lines represents magnetic field lines. Okay, so when you move this magnet, these magnetic lines means flux will change. Due to change in flux, here current induces. Okay, so this is first experiment, that is magnet and coil experiment, to demonstrate, that is electromagnetic induction. Now let us move to another experiment, that is coil and coil experiment. Coil and coil experiment means now you have to draw two coils. See the diagram here. This is one coil and this is another coil. Okay, so for one coil, this is C1. For this coil, you have connected one galvanometer. Okay, so galvanometer G is connected to coil C1. Now take another coil, that is C2. For that you have to connect the battery. Okay, so for one coil you have to connect galvanometer, and for another coil you have to connect the battery. Now what you have to do? C1 and C2 are two coils. C1 is connected to galvanometer and C2 is connected to a battery. When the coil C2 is pushed towards C1, means what? Once the battery is on, current flows through the coil. Which coil? C2, because the battery is connected to C2. Okay, so it becomes now current carrying conductor. As I told, around the current carrying conductor there exists magnetic field. Now you have to change this magnetic field now. How to change the magnetic field? Move the coil. So C2 is pushed towards the coil C1. Okay, so now in the C1, since galvanometer is connected, when C2 is moved, because of change in magnetic flux, current induces in the coil, that is C1. In C1, current induces and the galvanometer shows the deflection. Now what you have to do? C2 is pulled away from the coil C1. Now take out the coil. The galvanometer shows deflection in opposite direction. This indicates that the current is induced in the coil C1 in opposite direction. Okay, hope you are understanding. Let me repeat once again. In coil C2, battery is connected. Because of that one, current flows through the coil C2. Okay, so it becomes current carrying coil now. So around the current carrying conductor there exists magnetic field. Okay, so when C2 is moved towards C1, what happens? Magnetic flux, magnetic field lines, number of magnetic field lines changes. Due to this change in magnetic flux, current induces in C1. Okay, so in C1 galvanometer is connected and that galvanometer is showing the deflection. When C2 is moved away from the coil, when it is pulled away from the coil C1, again galvanometer shows the deflection. Okay, when two coils are held at rest or moved with zero relative velocity, the deflection in the galvanometer reduces to zero. So when both the coils are at rest or moved with same zero relative velocity, deflection in the galvanometer reduces to zero. Means what? Reduces to zero means what? Current is not inducing. Okay. The deflection of the galvanometer is large when the coils are moved faster towards or away from each other. See in this, hope it is clear. When current flows in one coil, immediately there is change in magnetic flux and the galvanometer is showing the deflection. See here. In coil A, since battery is connected, when switch is closed, immediately flux changes, and due to that flux change in coil B, galvanometer is showing the deflection. Okay? Yes. Now, result of experiments conducted by Faraday, and at the same time another scientist conducted the same experiments, that is by Henry. So result of experiments of Faraday and Henry. Means from these two experiments, what is the result or what is the conclusion? Just observe the conclusion here. Whenever there is a change in the magnetic flux linked with the closed circuit, an EMF is induced in the circuit. Current induces, EMF induces. So whenever there is a when current is present, definitely EMF must be present. Even reverse is also true. So when there is change in magnetic flux, EMF induces in the circuit, and this EMF exists, it remains as long as there is change in magnetic flux. This phenomena is called electromagnetic induction. See the result once again. Whenever there is change in the magnetic flux, EMF induces. This EMF remains as long as there is change in magnetic flux. This phenomena is called electromagnetic induction. Okay. Now let us see most important one, that is Faraday's law of electromagnetic induction. So let us see the statement. The magnitude of the EMF induced in a circuit is equal to the time rate of change of magnetic flux linked with the circuit. So what is the statement? The magnitude of EMF induced in a circuit is equal to the time rate of change of magnetic flux linked with the circuit. Mathematically, if we want to write it, magnitude of EMF is represented by E. E is equal to time rate of change of magnetic flux. For time you take it as dt. Change of magnetic flux d phi b. So E is equal to minus d phi b divided by dt is mathematical form of this statement. E is equal to minus d phi b divided by dt, where E is EMF induced in the circuit, d phi b divided by dt is rate of change of magnetic flux. And this negative sign indicates the direction of EMF E. Negative sign minus d phi by dt you have written. So negative sign indicates the direction of E. Okay. Just to understand the concept, one more slide here. This is C. When magnet is inside the coil, EMF induces, it remains till there is change in magnetic flux. And this induced EMF is equal to time rate of change of magnetic flux. Okay? Fine. Hope the points are clear. Let us continue. Thank you.